Hi, and welcome to Chapter 15, Ecosystems and Communities. So I guess we're going to start out with ecosystems and then move on to communities, but I suppose I should define ecosystems for you. Ecosystems is, well, okay, it's a little weird because it's based on this term community that you haven't learned. So an ecosystem is a community of organisms. That just means a bunch of different species living together in the same location. So an ecosystem is a community of biological organisms and really kind of focusing on the non-living parts or components of that world in which they interact. So the physical, or being schmancy here, we could call it the abiotic environment or non-living part of the environment. So we can talk about chemicals and any physical conditions like amount of rain and the water and the temperature, rainfall, things along those lines. We really just refer to those physical conditions as the habitat. So when we study ecosystems, we really tend to focus more on the physical abiotic environment, even though we're really talking about how the living things are interacting with that physical environment. And one of the major ways that we think about ecosystems is in terms of biomes. And a biome is just a large area that encounters the very, very similar environmental conditions, physical and chemical conditions. So there's a couple different ways we can think about biomes. Starting out with the terrestrial biomes, those are the land-based biomes. And you can see like all of the different biomes kind of striping across the globe here. And the land-based biomes are really based on two main considerations. That is the temperature and the precipitation, or amount of rain or snow and so forth. So when we think about temperature and precipitation, the first thing that we're going to be thinking about in the land biomes is how temperature and precipitation affects plant life. And so we can't just think about just temperature on any given day. We think about temperature throughout the day. We also think about temperature on a seasonal basis across an entire year, that kind of thing. And we think about precipitation in the same way, like how often does it rain? Does it rain relatively constantly throughout the year, or does it vary seasonally? And those are the kinds of things that are going to affect our biomes. So we've got our temperature and our precipitation. And I've already talked about plant-based life, but that's a little inaccurate because we're not just talking about plants here. We're talking about anything that is capable of photosynthesis. And so we have this category of organisms that are capable of photosynthesis, and they're called primary producers. And what they do through photosynthesis is called primary productivity. Basically, primary productivity is how much carbon dioxide and water is going to be combined into making sugar across a day or across a year. So we've got our primary producers that are capable of photosynthesis, and we've got you got your plants, but there's also bacteria and algae these are bacteria, these are algae that are capable of primary productivity or photosynthesis as well. So in this chapter, when I talk about plants, I'm actually really using that term very, very broadly, and I'm talking about anything that is capable of photosynthesis. So kind of keep that in mind as we go through. And yes, since we are talking about photosynthesis, you do need to learn the chemical equation for photosynthesis. It's not that challenging, so I'll step you through it. The first thing that you need is carbon dioxide, which is right here, CO2, that's carbon dioxide. I don't know if you know anything about chemistry, but any chemical equation is going to have a balanced, so whatever is total on this side is going to add up to the total on this side. I'll step you through that a little bit. Basically, you just need to memorize this equation, but for those of you who are interested, I'm going to give you a little bit of detail. So you've got these 6 carbon dioxide molecules, and you're going to combine them with 6 water molecules, that's H2O, and you need some energy to do this. Needs a lot of energy input. In the case of photosynthesis, your energy input is coming from sunshine. So sunshine is the energy that's going to allow you to combine carbon dioxide and water. And from that, you are going to make this sugar right here. This is glucose. And you're going to have some leftovers here. This is your waste product, and that's oxygen, which is important to know. Oxygen is a waste product of photosynthesis. So just for those of you who are a little bit more interested, if I count up how many carbons I have in CO2, there's one, but I have 6 carbon dioxide, so there's 6 carbons on this side. And if you look over here at this sugar, all of those carbons go into that sugar molecule, that glucose, C6. There's 6 carbons in glucose. If you look at how many hydrogens there are in water, there's 2 hydrogens in every single water molecule, but I've got 6 water molecules, so that equals 12 total hydrogens, and all of those hydrogens go into the sugar molecule. If I look at oxygen, I've got 12 oxygens here, and I've got 6 oxygens here, and I've got 6 oxygens here, and I've got 6 times 2, or 12 oxygens that are in the waste product. So a nice balanced equation for photosynthesis. The reason we talk about this is because we are going to be talking about the carbon cycle a little bit later, and so it's important for you to know about. We'll also be talking a lot about energy in a little while. So that's what primary producers do. They do photosynthesis. And then, of course, we will be talking about food chains eventually, and food webs and so forth. And so what happens is that anything that eats a primary producer is going to take that energy in the form of glucose or sugar, which you see right here, and it can only do it if there's oxygen around. So it's going to take this glucose, add a little oxygen, and it's going to make energy in the form of ATP. I know we haven't talked about ATP for a while. We talked about it back in chapter 3, we talked about it in chapter 5 a little bit, but it's coming back to revisit us in chapter 15. So the main goal of this process called cellular respiration is to get energy in the form of ATP from food, and in this case the food is in the form of glucose. So we've got oxygen and glucose, and that's giving us some waste products of carbon dioxide and water. If you're very, very clever, or maybe you've learned about this before, you might notice that the equation for photosynthesis and the equation for cellular respiration are opposites of each other. Let me just go back and show you that we've got our 6 carbon dioxides and 6 waters plus a little energy gives us sugar and oxygen. And cellular respiration is 6 oxygens and 6 sugars, gives us some waste products of carbon dioxide and water plus that energy that we really, really need to survive. All right, this is just a little background information for you so that we can continue our conversation about primary production and terrestrial biomes, and let's take a look at that. So our terrestrial biomes, there's 9 of them that your book brings up. Some books talk about more and some less. I'm just going to briefly step you through some of these biomes, talk very briefly about the conditions that go into affecting these biomes, and specifically focusing here on precipitation and temperature. So a tropical forest, like a tropical rainforest, and this is color-coded for you, so if we go up here in the red areas, you can see where the tropical rainforests are. They tend to be around the equator. We'll talk about why that is in a little while, but mostly what you get in a tropical rainforest is lots of rainfall and a hot temperature that turns out to not be super duper crazy hot like you might get in a desert. Deserts are color-coded yellow, and you can see that there's a lot of deserts in the northern hemisphere, and you're going to find some in the southern hemisphere as well, just south of that equator. As you might know about deserts, they are very hot and they are very dry. We'll talk about why they're so hot and dry in a little while, but just kind of remember that we are focusing right for now on just precipitation and temperature. This is a savanna. You'll find the savannas in the pink areas of the map. So savannas around there, a little bit of savanna over here. And savannas are also quite hot. They're near the equator, but they get seasonal rain. So they have a wet season and a dry season, and that's a pretty big deal for savannas. There are also really a lot of fires that go on in savannas during the dry season, and that helps control the growth of primary producers. Our next is the temperate grassland. And you find temperate grasslands in orange. So we've got some in the northern and southern hemisphere, and they tend to be in this little stripe located around here. We even have a little bit of that in Australia. Temperate grasslands have seasons because they're far enough north away from the equator that you get seasons. And so winter and summers, there's a moderate amount of rainfall that happens in these temperate grasslands, not a lot of trees. Temperate deciduous forests, those are forests where trees lose their leaves, and you're going to find those in green on this map. So a little temperate deciduous forest right here. We actually in Illinois live on the border between a temperate deciduous forest and a temperate grassland. But over in Europe, the kind of Western Europe that we think about, that was once just completely temperate deciduous forest. A little bit over here in Asia, and a little bit on the coast of Australia. Temperate deciduous forests also have seasons. They're a little bit more mild than the temperate grasslands when it comes to winter temperatures, but they have about the same amount of rainfall. The next is the chaparral. Most of you haven't heard of the chaparral. It's in purple in this map, and the main areas for chaparral are going to be around the Mediterranean Sea. You get a little bit in Australia as well, and you might find some chaparral in the mountains in the western United States. Chaparrals are hot and dry, but not as hot as a desert or a savanna. They're usually a little bit wetter as well. So you get low growing shrubs, not a lot of big tall trees because not enough moisture, but it is quite warm. Again, not as warm as a desert. The next is the coniferous forest. You might have heard the term boreal forest. That's in the darker blue stripe that swaths across Canada, Northern Europe, and Russia. And the coniferous forest is an evergreen forest. Very cold in winter, moderate to warm in the summer, lots and lots of precipitation, but usually in the form of snow. Our next one is the tundra, and you can see tundra on our map up here in the far northern Canada, far northern Europe, and Russia. And tundra does get quite a bit of moisture, but it has something called permafrost. And permafrost just means that the ground is permanently frozen. As global warming is happening, this permafrost in the tundra is actually becoming less and less abundant. The permafrost is shrinking, and so there's less area that's permanently frozen. And what that means is that trees can start to grow in the tundra. It also means we get a lot of release of methane, which contributes to global warming. It's this vicious cycle we'll talk about a little bit more when we get into chapter 16. Finally, there's the polar ice, and you can find polar ice in Antarctica and in Greenland and far, far northern Europe over there. And polar ice, you'd think, because there's a lot of ice, that means a lot of precipitation, but you would be quite wrong. There is not a lot of precipitation at the polar ice caps. There are basically very, very cold deserts. And so any water that happens to be in the air, any moisture that happens to be in the air will freeze, and that's how you get these polar ice caps. So desert-like conditions when it comes to precipitation. The aquatic biomes are interesting. Aquatic biomes are determined not by temperature and precipitation. Aquatic biomes are determined more by salinity, that means how salty the water is, how the water moves, and how deep the water is. So our first one are lakes and ponds. And again, if you look at our map here, there's lots of lakes and ponds all over the place. It's hard to see them on a map, so this is kind of really focusing on the big lakes, like the Great Lakes up here, and some of the lakes in Canada that are easy to see from far away. In general, lakes and ponds tend to be not salty. They tend to not have water movement, and they tend to be shallow. Generally speaking, shallow. Some of them can be kind of deep, like going down 300 feet, but that's a rarity. Most lakes and ponds are shallower. The next are rivers and streams, and you can see like there's the Mississippi River right there. You can kind of see the Missouri and so forth. Rivers and streams tend to be freshwater, have linear water movement, and to not be very deep. I know this throws off a lot of people because if you think about like the Mississippi River, a lot of people have the misconception that the Mississippi River is a really deep river. But on average, the Mississippi River is pretty shallow, um, around 10 feet or so, not much deeper than 10 feet on a good day. The next one is the open oceans. And of course, that's the darker purple, that's basically surrounding everything. And the open oceans have high salinity, that means they're salt water. They have water movement, but that water movement is circular, and we'll talk about what that looks like in a little while. And their depth is very deep. These can go up to a mile deep and so forth. Our next category are estuaries and wetlands. And estuaries and wetlands can be either saltwater or freshwater. It depends on where you're looking. But for example, here's the Chesapeake Bay, which is an estuary. And estuaries tend to be a mix of saltwater and freshwater. But wetlands in general can be anywhere, honestly. The water movement is stagnant or kind of tidal, meaning it'll move in a little bit during the day and then it'll move out a little bit during the day. And the depth is very shallow. Coral reefs is our last one, and we can see the coral reefs here along the coast of Central America, around the Caribbean islands and so forth, get a little bit around Florida. And coral reefs thrive in mainly shallower water. Photosynthesis is a pretty big deal for those coral reefs. So a little bit on the shallow side, got to have light penetrating in order for those coral reefs to be healthy. They are in salt water. And for coral reefs, we tend to say that the water movement is tidal. That means the water moves, it rises and lowers during the day. Okay, well, hopefully the aquatic biomes make a little bit of sense, and we do define them differently from the terrestrial biomes. So, what factors are influencing the biomes? And there's a couple of them that we're going to focus on here. We're going to really be thinking about how global air circulates. And the things that, I mean, I know this is going to sound a little funny the way I'm wording it to you, but the things that affect air circulation, which of course affects temperature and rainfall, are twofold. Number one, the earth is tilted, and the tilting of the earth affects the seasons. Also, turns out the earth is round. No matter what the celebrities are saying these days, the earth is in fact round, and it's the roundness of the earth that influences temperature. So I'm going to step through both of these with you. We're going to start out with the tilting of the earth. And the earth is not, if you think about where the sun is, the earth isn't like a 90-degree angle towards that sun. It's tilted 23.5 degrees. And because of this tilt of the earth towards the sun, sometimes the northern hemisphere is tilted towards the sun. That would be summertime. And in our summertime, the southern hemisphere is actually tilted away from the sun. That gives them a wintertime. And the opposite of true, of course, is true, of course, for our winter. In our winter, we are tilted away from the sun, so we're not getting as much sun energy. And the southern hemisphere is tilted a little bit towards the sun, so they get more sun energy, and they have their summer. On the equinoxes, that's where the days are equal in length. We are at basically a 90-degree angle. And it has to do with this rotation of the Earth around the sun. Yes, I'm sorry if I'm the first person to tell you, but the Earth does, orbit around the sun and not the other way around. Copernicus was right. Go Copernicus. Okay, so sorry about that. So the next thing is that that I need to tell you is that Earth is in fact round. This is important because the way that the sunlight hits the Earth is different depending on where you are located on the Earth. So for just a second, let's think about the equator. At the equator, which is for the most part of the year, it's the region that's kind of curved closest towards the sun. You can see here, and so the rays of the sun, when they hit the area of the Earth that's the equator, are really dense in energy. However, if you think about how that same amount of sunlight hits farther up around the curve of the Earth, like the northern hemisphere, that same amount of energy that's hitting the equator is spread out farther on the Earth's surface. And so there's less energy per square area hitting the Earth up here compared to here. So lots of energy here, less energy in the northern hemisphere, and less energy in the southern hemisphere. It's spread out over a larger area, and so the equator is warmer. That's why the equator is warmer, because the Earth is round. So whoever is saying these days that the Earth is flat because that's the way it looks, they know nothing, literally. All right, so Earth is tilted and Earth is round. This contributes to temperature and to rainfall, and that's what we're going to explore next, is exactly how this rain happens, how this rain forms. So it's a little complicated, but it's not too bad. So the first thing that you need to know is that when the sun hits the Earth, it's not actually warming up the atmosphere itself. The atmosphere is too diffuse for it to warm up much. It's actually the sun is warming up the surface of the Earth, including the land and the water. And when that land and water heats up, as we know, warm air rises. And so what we get here is this warm Earth. The surface temperature, again, it's not warming up the air up here, it's warming up the surface. And it's that warm air, that's the warm Earth, that is forcing the air to rise because warm air rises. But of course, here's the conundrum. As that warm air rises, it gets farther and farther and farther away from the source of the heat, which once again is the Earth warmed up from the sun. So warm air rises. As it gets farther and farther away from this warm source, it cools down. And here's the thing about cold air. Cool air cannot hold as much moisture as warm air. And so we get rain. The cool air drops its precipitation, drops its moisture, and that's why it rains. So I personally think that's kind of cool. Like the sun is driving, it's the energy that's driving all of this rain and moisture and precipitation and temperature, and they're completely related to each other. And this is why we get biomes. Okay, so hopefully that makes sense to you, because we're going to start talking about how this rain forming affects primarily two main biomes. We're going to first talk about the tropical rainforests, and then we're going to talk about deserts. So just to remind you, tropical rainforests are in red, and deserts are in yellow. Okay, so let's take a look at this view. And remember, the sun is shining on the equator most densely, so we get the most amount of energy on the equator. And we just learned that warm air rises, so we're going to get a lot of warm air following the arrows. We're going to get a lot of warm air rising, and of course, warm air rising gets farther and farther away from that source of radiant heat, the Earth. And so it starts to cool down, and that's what the blue arrows are, that's cooling down. As that air cools down, it drops its rain. So where do we find those tropical rainforests? We find them at the equator. Make sense? So lots and lots and lots of rain here because there's lots and lots and lots of sun hitting the equator, lots and lots of energy. All right, let's continue following these arrows though. That cool air rises, and it rises and it's got to go somewhere. The cool air, now that it's cold, it's more dense, and so the cold air is going to fall somewhere. And you might think that the cold air might start falling here at the equator, because why would it go anywhere else? But remember that it's kind of still being forced up by the warm air that's kind of pushing that air up. And so it's got to go somewhere. So the air mass splits in two. Half of it goes north and half of it goes south. And let's just focus on the northern hemisphere for now because that's where we live. So the cool air is moving along, circulating along, being pushed up by this, I don't know, like a hot air hair dryer or something, being pushed up, and it's got to go somewhere. And where it does is it falls eventually back towards the earth at 30 degrees north, and of course at 30 degrees south. So as this cool air starts falling towards the earth, it starts to warm up because remember that sun is shining on the earth and it's warming up the surface. And so as this cool air approaches, as it falls down towards that surface, it gets warmer and warmer and warmer. And as it gets warmer and warmer and warmer, it clearly starts to heat up. But notice that there's not a lot of precipitation. There's not a lot of moisture in this air. It lost all of its moisture here at the equator. And so what we get is a lot of dry, hot air at 30 degrees north and 30 degrees south. And if we look at our map at 30 degrees north and 30 degrees south, we see deserts. Now, it looks really good at 30 degrees north and south in Europe, and that makes sense. We'll talk about why it looks a little bit strange in North America and South America in a little bit. But for now, just focusing here on this little stripe of 30 degrees north and south that we see, except for the Americas. And those are the deserts. Deserts are hot and they are dry. And that hot, dry air is formed by this warm, moist air losing its moisture, circulating around, coming back to falling down at 30 degrees north and 30 degrees south where it gets really, really warm. And that's how you get a desert. Now, there's other things that influence weather as well, weather and ecosystems as well. A little bit of these are small scale, some of them are a little bit larger scale. I'm going to step through all three of them that your book brings up, including there's some modern influences to weather, and that is the heat island effect. That's your term. It's not written here, but that's the term we're going to talk about is the heat island. So a lot of asphalt and cement and buildings will trap heat very, very efficiently. And so it turns out that cities are much warmer by several degrees warmer than the surrounding countryside. And so we get a little bit of heat island effect going on. Another thing that modern landscapes do is that they create windy conditions. So what tall buildings do is they force the air that's flowing through to go up and then go down, and that causes wind. We think about Chicago as being the windy city, but if you've ever walked around downtown St. Louis where the tall buildings are, you're going to experience that same kind of windy conditions. It is very windy in Chicago, don't get me wrong. But the main natural formation of affecting of weather on a slightly smaller scale than the entire globe, but it's kind of a big deal, is the formation of rain shadows. And rain shadows, that's your term, form in the presence of mountains. So if we look at a set of mountains, like it might be easy for you to think about Seattle, that if you've ever heard of Seattle being a very rainy town, or Portland, you might know what I'm talking about. So those are on the western coast of the United States. And what happens is that warm, moist air coming off of the Pacific Ocean goes across the land and is forced upwards. This should sound very, very similar to what was happening over here at the equator. So that warm, moist air is forced upwards, and of course, when it's forced upwards, it gets farther and farther away from the main land mass, and it cools down, which means that it drops its moisture, cools down, goes over the top of the mountain, gets closer and closer and closer to that main land mass, but it lost all its moisture over here. And so we've got hot and we've got dry air on the far side of the mountain, and we have wet, moist air on this side of the mountain. So if you look over here on the west coast of North America, you'll see a little bit of very wet area over here. And you've got this very large and really goes far north desert that extends, it's just very extensive. And of course, you've got your mountains right here. And it's these mountains that are contributing to the extent of this desert. There's actually 5 deserts in North America. I'm not going to name them for you, but the one that goes really, really far north here is the Great Basin. And that is the one that's really affected by this rain shadow concept. Although they all are affected by it, but we've got this issue here of the deserts. So you might also be wondering why that desert doesn't extend all the way across North America, like you see here, it extending across Northern Africa and the Middle East. And that in part is forced by the Gulf of Mexico that you see right here. And the Gulf of Mexico has some wet air coming in, a wet air mass coming in this way, which contributes to our grassland and our temperate deciduous forests. And we'll talk on our next slide about how water circulation affects temperature and precipitation as well. And I'm just going to go ahead and take the break now. It's been about 30 minutes. So we'll take a break and come back to thinking about how ocean currents affect weather.